Okay, good afternoon. So this afternoon we'll be concluding the talk content on this module, and we'll be moving to the revision lectures afterwards. So the two topics we're going to be covering in these following 2 hours will conclude the camera geometry work. The first hour we're going to talk about this process of camera calibration. Who remembers what we mean by camera calibration? Estimating the camera parameters, that's right, yeah. And by that we mean the intrinsics and the extrinsic parameters of the camera, yeah. So you've talked a little bit throughout, well, the last 3-4 hours of lectures about how we have this process for doing that. Well, now we're going to talk about that process. And then in the second hour, we're going to look at a case study, actually seeing how these techniques and others we've encountered on this course are integrated into building this studio that I mentioned previously that we have here on campus, this multi-view studio for 3D reconstruction of performance. And that's just really a case study to show you how to build a computer vision system and how a lot of these things can pull together. So in this first hour then, for which I've distributed the handouts, the learning outcomes are, first of all, to understand how this projection matrix for a camera is constructed. We've touched on that and we're going to return to it and see how it encompasses the intrinsic and extrinsic parameters of a camera. And then we're going to see how we can directly recover the projection matrix from observations of a known prop, like a grid. Okay. And then having recovered that, we'll see how we can decompose the projection matrix into its intrinsic and extrinsic components, and we'll see how we can integrate some of that with the fundamental matrix work we covered last week to create a robust camera calibration. And we'll finish with a brief talk about stereo rectification and canonical viewpoints. Okay, well, let's just recall a few things that we covered last week then. First of all, I introduced to you the epipolar geometry, which, if you remember, is some reasoning about the content observed by a couple of cameras imaging a 3D object. Now, if we know the calibration of those two cameras, which here we've called the left and the right camera, but they can be anywhere, then we can do things like reason about the possible locations of one point from another viewpoint. So if I were to view the top of that tree here on the left-hand camera, and that's my location of it, my x1, y1, then all the possible locations of that point along that ray of light form the image of a line in the right-hand camera, and we call that the epipolar line. And this equation here encapsulates that relationship. It says that a point, for example, on the left-hand side in homogeneous form, multiplied by this 3x3 matrix F that we call the fundamental matrix, multiplied by any of those locations along that epipolar line on the right-hand side will give us 0. And vice versa. So I could have put the right-hand point in as a single point and reasoned about all possible locations in the left-hand camera. It's that relationship there encoded by that 3x3 matrix, the fundamental matrix, that encapsulates everything we know about the relative positions and internal parameters of those cameras, what we call the extrinsics and the intrinsics of those cameras. What are examples of the intrinsic parameters of a camera? Anyone? Focal length, thank you. And optical center, yeah? Okay, which is that offset on the image plane. And what about the extrinsics? The position of the camera. So its position of its focal point, which is often expressed as a translation, and its orientation, which is expressed as a rotation. Yeah, that's right. So the position of the camera are the extrinsics. Okay. So we went through the derivation of the fundamental matrix in the previous hour, and we saw that from that derivation, that F is comprised by multiplying 3 matrices together. The camera calibration matrix of the first camera, which we're calling the left camera on the previous slide. Okay, we'll look at the format of that in a minute, but it's basically a 3x3 matrix that encodes all of those intrinsic parameters. Okay, and it's going to be inversed and then transposed. That's what that minus t is shorthand for inverse transpose, multiplied by this E, and then multiplied by the inverse of the camera calibration matrix For the second camera, or right-hand camera, which has the same form, it encodes the intrinsics. So what does the E encode? The extrinsics. And E is what we refer to as the essential matrix. And the format of E, oh no, we haven't got that yet, it's on the next slide. Start with the format of K. This is the format of K. So this is, as I say, the camera calibration matrix. The intrinsics matrix for each camera is encoded with the optical center on the right-hand column, acting effectively like a translation in 2D, which is of course what it is. We discussed that last time. And the focal length acting as a scaling factor down the diagonal. And you can see that because it's in this form, we can talk about independent focal lengths for X and Y coordinates. So what does the format of E then look like? Again, we showed this last time. E is effectively the rotation and the translation, encoded as a rotation matrix multiplied by this cross-product encoding of the vector t. So t is the translation of the camera's focal point of some reference, like the origin of the world, and t then is pushed through this rearrangement here. So imagine, so t is what the x looks like in this red box. Its components get scattered in this way, such that it has the effect of making a cross product with the vector it's multiplied with. So E encodes the essential matrix. So in this setup, just to sort of reiterate what we talked about last week, in this setup, when we talk about the intrinsics then of each camera, they're independently defined. Each camera can have its own focal length, its own optical center. That's why we've got two Ks in that equation, the K1 and the K2. But the extrinsics encode the relationship, the relative position of the right-hand camera, so camera 2, with respect to the left-hand camera. Okay, so the R in this case that goes into the essential matrix is the relative orientation of the right-hand camera to the left-hand camera. The rotation we need to make to turn the left-hand camera to align to the right-hand camera. And the T is the shift that we would have to make to move the origin of the left-hand camera to the right-hand camera. Okay, so it's important to recognize that when we're talking about the fundamental matrix and the epipolar geometry, the extrinsics aren't encoding each camera's relative orientation and shift off the origin of the world. The origin of the world is effectively the focal point of the left-hand camera, and the orientation of the world is aligned to the left-hand camera, and the R and the T are just encoding that right-hand camera. Okay, does that make sense? Right, so in the previous lecture, lecture 24, we showed how it's possible to estimate this F, which is just written out in longhand here, directly using 8 pairs of corresponding points across these two images. Do you remember? We established SIFT correspondences, and then we used RANSAC to estimate the best fit homography to correspond to those SIFT points. So this process, if you recall, we call it a weak calibration, because we're directly estimating the matrix F here. We're directly estimating that matrix F. I showed you this example when I had my little program that was putting those yellow correspondences between two photos from holiday. Yeah, that was performing weak calibration. It's called weak because we can't decompose without further information that F to get our intrinsics and extrinsics. It just comes to us in that 3x3 result from the 8-point algorithm that we discussed last time. So if we want to get a strong calibration, if we want to actually know specifically the intrinsics and extrinsics, such that we could, if we wanted to, multiply them together to make that F, then we need to do something else. And that's called strong calibration, and that's the point of the talk today. Okay. Why would we want to do that? Because if we know K and E separately, then that gives us our focal lengths and optical centers and our R and our T that enable us to do things like do 3D reconstruction or triangulate points. If you remember, these two applications that we covered in lecture 23 involved those two sets of equations in the purple boxes. Do you remember? One took us from 2D to 3D, one took us from 3D to 2D. both of those boxes required us to know explicitly the focal lengths, the optical centers, the rotations, the translations. So we'd need a strong calibration to do these things. It's not enough just to do a weak calibration and estimate the F directly. That's why we need what we're talking about today. And in fact, there are the equations. Okay, so let's remind ourselves then how camera projection works. We're going to model this, use the camera as a pinhole camera. We're going to model the process of perspective projection. Just to recap this, because we've covered it already, perspective projection is all based around similar triangles. If we have an object, in this case it's a tree, it's at a height y, and it is some distance z away from the focus of our camera, then we can reason about the height, the apparent height of that tree on the image plane, which is y prime, using this ratio of similar triangles. So we say that y prime over d is equal to y over z, and then if we multiply both sides by d, then we get this expression which directly lets us recover the apparent height of the tree on the image plane, and we could do this for x as well. And this transformation is encoded in this 4x4 matrix transformation here, and we also covered the shorthand version of this as well. Why do we have a shorthand version of this? Because we don't care what the z coordinate is after this projection. We're going from 3D to 2D, so we're dropping the third row of that matrix in the 4x4 format. Yeah. So if we calculate through, what we get is d times x, it gives us dx, d times y gives us dy, d times z gives us dz, and 1 times z gives us z, so the homogeneous coordinate is z, so to get the location of the points after our projection, we divide through by that homogeneous coordinate, and you can see that the third value there is just dz over z, so basically it's d, so everything's being projected onto the image plane at d, which is what you'd expect in this construction. So that's why we just use the shorthand version, because we don't care about that, it's the answer just d. Okay, now we saw that if we want to reason about that construction anywhere, so with any positioning of the camera, not just a camera at the origin pointing with its optical axis down the z-axis, then we need to think about these extrinsics that we talked about before. So if we project a point in 3 dimensions to 2 dimensions, its image is p prime, then we're going to talk about some positioning of the camera relative to the object given by r and t, and then a projection. And this compound matrix transformation is this pi matrix, which we've come across before. We're going to return to it today. We call it the projection matrix, camera projection matrix. And you can see how it's composed. We've got this section here at the end, which is our t, which is just the identity matrix with this negative c here. This is our camera offset from the origin. R is our orientation, so that's our extrinsics, and our intrinsics then are encoded into our k in the same format I just gave you, which you can see has a scaling effect then on the first 2 rows of that matrix, and a shift on the optical center. Okay, right. So that was all a bit of a recap, but important to have it fresh in our minds, and useful perhaps to recap it anyway, because now we're going to talk about how we estimate this camera projection matrix directly from observation. And the way that we're going to do this, well, first of all, why are we going to do this? Because as I'll show you in a moment, if we can estimate pi, the camera projection matrix, directly, then it is possible to decompose that pi into the intrinsics and extrinsics directly to give us a strong camera calibration. Okay, so how are we going to do that? We're going to do it by observing, again, corresponding pairs of points, but this time between 3D and 2D, and we're going to use a known what's called calibration prop or object in order to do this. So in this photo, we've got a calibration prop, and it comprises 3 planes. Well, this is a bit of a funny prop actually, because it doesn't actually have the planes completely orthogonal, but normally you would, or maybe it's just the camera angle, I'm not sure. But anyway, let's say it comprises 3 planes oriented to the 3 axes of the world, and that gives us a convenient way to obtain 3D coordinates for points on that object. And these, in this case, have been painted onto the object as little white dots. So in this system, the origin of the world, once we've calibrated our camera, is going to be defined as the very corner of that calibration object, right in the middle there, okay? And then those dots, if those planes are orthogonal to one another, then those dots give us a very convenient way to establish a 3D coordinate system, right? Because I can say, well, that dot there, it's one move along that plane and one move along that plane and no moves along the other plane, for example, yeah? So the dots then we can come up with simple coordinates for them, like 1, 0, 0, 2, 0, 0, and so on, all right? As I say, in this particular construction, they seem to have decided to make their lives a bit more complicated by not doing that, but usually you would do that. So okay, so what we've got here then is an object we've manufactured. You know, we've gone down B&Q, bought some chipboard, painted it. Is usually what we do, and we paint those dots on. And for every dot, we've got a position then in our invented 3D world coordinate system where the origin of it is that box. Yeah. Okay. So. Right, and that's what this slide is saying. So yeah, the inner coordinate is the origin, and the 3D coordinates are known by design. Now, as I say, what we need to do is establish a set of these observed points in 3D and see where they correspond to in 2D when we've taken a picture of this object. So we built our object. We're going to take a picture of it with the camera that I want to calibrate, and then just by looking at that image, we can figure out where those points are. So, for example, if I've created here, a dot on my object and it's at location 1, 0, 0 in 3D according to my coordinate system I've built, I might observe that point is at location 200 by 100, pixel coordinates 200 by 100 in the image I've taken. All right. So it's trivial then to come up with a set of points in 3D and their corresponding pixel locations in 2D, yeah? And these are the sets of points mapping from 3D to 2D that we're going to need in order to directly estimate this matrix pi, okay? Right, is everyone following that so far? Yeah? Okay, good. Now, obviously you could automate this process, you could do it manually. I mean, you could just look at the image and just manually click on it, which is fine. If you want to do it automatically, then you can trivially write a little detector algorithm that goes over the image and finds the points in it, using a template or something like that. But the details for that are unimportant for today. Okay. So what we're going to do then, in order to estimate this or recover this matrix pi directly, is use these correspondences between known 3D points, which we're going to refer to as x, y, z for a given point, and known 2D points that we've imaged of those 3D points, which we're going to refer to as u, v. And this matrix here is the matrix we want to recover, the pi. We're going to use its shorthand form, and you'll observe that there are 12 parameters there that we need to estimate. Okay, so the m's are the things we want to find, and the x, y, z, and u, v are the things that we know. And because we're working in a homogeneous coordinate system, on the input side, on the 3D point, the homogeneous coordinate will be 1, and on the output side, following the projection, the homogeneous coordinate will be arbitrary. Let's call it alpha. So, we should refer to our output points as alpha u, alpha v, and remember that we have to divide by alpha to get their true location. Everyone following this so far? Okay. Oh. Sorry. Yeah. Right. So, the first thing we can do is write out the terms for alpha u, alpha v, and alpha. This is fairly straightforward because what we're going to do is just take this matrix here and just multiply it by the column vector, which is our 3D point input in homogeneous form, to get each of those terms. So, alpha u is obviously going to be m11 times x plus m12 times y, m13 times z plus m14 times 1 gives us this row here. So alpha u then is equal to this first row, alpha v the second, and then alpha this third. And just like, well, almost just like, because it's not the same as homography, just like when we were looking at the homography situation of recovering the homography, we noticed that we can immediately substitute the alpha in to the first two equations in order to remove that equation. Does that make sense? So if I were to take this term here, this third term, which is alpha, I can just substitute it here, so it's v, and then all of this in brackets, u, all of this in brackets, to get two equations there. So we've got two equations and 12 unknowns, so we need 6 pairs of points to solve it. Yeah. So there we go. This is exactly the rearrangement I was talking about there. So in the brackets there, we have the term for alpha from the previous page. So u alpha equals, and then the first line of that vector, v alpha equals, then the second line of that vector on the previous slide, and they are two equations. There are two equations with our 12 unknowns in them. Everyone following so far? Yeah? Yeah? And then we're going to, just like we did with the homography, we're going to just subtract one side from the other to get an expression equals 0 for both of those lines. Okay, so we're going to have, let's subtract the left-hand side from the right-hand side. So we're going to have m11x plus m12y plus m13z plus m14 minus um31x, and so on. Okay. So what we're going to do then is form one of these homogeneous linear systems again, where we have a big design matrix A, x are our unknowns we want to solve for, equals 0 in this case. And we're going to just look at the coefficients on m11, m12, all the way through to m34, and just populate that design matrix with those coefficients. Okay, so again, let's have a look at the first line. You know, how many lots of m11 are there? X, m12, y, m13, z, m14, 1. So you can see how we're populating the first row there of the design matrix. How many m21, 22, 23, 24s are there in that first line? None. So 0, 0, 0, 0. Okay, and then how many lots of m31? Well, because we subtracted it, it's going to be minus ux, minus uy, minus uz, minus u. Yeah? And then for the second line, I won't talk it through, but you can see there's no m11 to m14s. And similarly, we've written it out to create those terms. Yeah? So we've got two rows there for a single correspondence from 3D to 2D. That's a point we painted on our object that we know the coordinates of by design, and the image of it that we've recovered from our 2D photo we took of the object with our camera that we want to calibrate. Okay, and we're just going to replicate those two rows basically 6 times, so we have 12 rows there in the design matrix, and we're going to do that for each of those pairs of corresponding points from 3D to 2D. So we need 6 of them to get enough to solve our linear system. Does that make sense? Yeah? Any questions on that? Everyone okay with that? So it's a very similar way we're forming this design matrix as when we estimated the homography, but just to stress it one more time, we're not estimating a homography here, we're estimating the camera projection matrix pi. It has 12 unknowns, not 8, and the point correspondences are from 3D to 2D here, not from 2D to 2D, which was the case with the homography that estimated, you know, a plane-to-plane transformation. Yeah. Okay, so once we have our design matrix populated, then we simply solve using SVD, as we did with the homography, and we are effectively looking at the last column of V, the eigenvectors that the SVD algorithm gives us, and that gives us our solution, our exact solution to this problem. And if we were to include more point correspondences, then our X would be a best fit solution in a least squares sense. Yeah. Okay. Right. So, and that's it. So we've recovered then our camera projection matrix using that known calibration objects comprising multiple planes. We've taken one photo with our camera, and we've recovered the camera projection matrix. So now what we're going to do is look at how we can decompose that camera projection matrix to recover our intrinsics and our extrinsics. Well, in order to do this, I'm just going to show you the equations. So first of all, just a shorthand notation, we're going to refer to the final column of that camera projection matrix as Q4, and then each of the rows of the 3x3 matrix on the left-hand side that kind of that makes up that matrix, we're going to refer as Q1, 2, 3 for the 3 rows. Okay, as has been written there, and we're going to take those to be column vectors, each of those. So then we're going to first of all recover the camera optical center. So this is one of the intrinsics that we can get via this process. And that is the inner product, the dot product between Q1 and Q3. And that's for the X component. For the Y component, it's the dot product between Q2 and Q3. And then to get the focal length, it's going to be the dot product of Q1 with itself. Okay, so the magnitude of Q1 squared minus the optical center X component squared, square rooted. That's the focal length for the X coordinate, scale factor on X, and then similarly for Fy, we're going to just do that, but with Q2 and Cy. So with these, pulling out these components of the camera projection matrix and rearranging them in this way, we recover these four numbers, which we then can populate our K with to get our camera calibration matrix, our intrinsic matrix that encodes the internal parameters of the camera we used to take that picture. Okay? Yeah? All right. Right, okay. I mean, some of you may have seen that there are other ways of doing this. You know, in OpenCV, which is a popular computer vision library, there is a routine there that will input multiple images and basically do recover the intrinsics, the K. Actually, it's pretty much the same process, but instead of taking a single photo with multiple planes in it here, we're taking multiple photos of single planes and then reasoning about their coordinate systems. But there is a slight difference, but we won't go into this particular method, just to sort of make you aware. Okay, so if you recall the format then of our camera projection matrix, which is there on the top, we've seen it multiple times now. We've seen now how we can recover our K directly from that pi that we've estimated via this approach. Looking at the way this multiplies together, we can see that this first 3x3 section of that matrix is given to us by KR. And the final vector is given to us as negative C pre-multiplied by R and K. So immediately we've got an expression there just by looking at the contents of that 3x3 matrix on the left-hand side. We've got an expression for KR, which is going to enable us to recover this C, which is our translation vector. So, you know, if we were to write, for example, KR just as shorthand as A, then we can say, well, our A then is our 3x3 section. Our right-hand column is negative AC. So C is just simply negative A inverse of multiplied by that final column vector. So we can trivially recover the translation component of the extrinsics. Okay, which, if you recall, are equivalent to the coordinates of the camera's center of projection, its focal point. Yeah. And then, you know, if we have this K in R, well, we already know K because we recovered it a moment ago. So if we know our K, then it's simple to recover our R. Our R is just simply K inverse A, and that gives us our orientation. So from our P, our projection matrix, which I don't know why it shouldn't be P, that should be pi. Symbol font's gone from the slide. We recovered the estimates of the extrinsics, our R and our T, and our intrinsics. So we have the full, strong camera calibration now that will enable us to do our, you know, for example, 3D object reconstruction or our point triangulation. Now, in this process, we have recovered RT and the intrinsics K from a single matrix. However, that can be quite an unstable way to recover particularly the extrinsics. It's subject to a lot of sort of numerical error and an error in measurement of these points, derived from the errors in measurements of these points. So what you can do, and is preferred to do in practice, is use the process I've outlined today to estimate your K, your intrinsics, but then use the weak calibration process that I outlined previously, the 8-point algorithm of the Ransack, to estimate your F, which encodes the intrinsics and the extrinsics, and then factor out the intrinsics from F in order to get your E, your essential matrix that encodes the extrinsics. Okay, so I'll just go through that process. So if we want to recover the extrinsics given an f and a k, the k being obtained through the method I've just outlined today, decomposing the elements of the camera projection matrix from those 6 corresponding points, and the f obtained using the method I outlined in lecture 24 in the previous hour, where we're using the 8-point algorithm to estimate f, or a robustified version of it using RANSAC. Then, because we can write our f, as we saw from the derivation last time, as the k for the left-hand camera, inverse transposed, multiplied by our essential matrix, which encodes the extrinsics, multiplied by the inverse of our internal parameters for our second camera, then we can just obtain our E directly by pre-multiplying this by the inverse of k for the left-hand camera, and here by post-multiplying it by the matrix that contains the intrinsics for the right-hand camera, which then cancel out those two terms and just leave us there with our E. Yeah? So if we've estimated our f via weak calibration, we can upgrade that to get the extrinsics out for a strong calibration if we have knowledge of our k, which we do using this camera calibration process I've outlined today with the grid. Okay, does that make sense? So, actually, I'll see if I can show you, it's quite a cool demo, well, video, that I might be able to show you of a product that Microsoft produced. Oh, now what was the name of the paper?
You can think about what photosynth does as linking images together. Whenever images are taken into a common three-dimensional environment, here's a point cloud, a model that's been reconstructed from all of those images.
What this software does, and this came from an academic paper that from Microsoft Research that they subsequently commercialized, is basically you take a whole bunch of tourist photos off Flickr or the internet, and then you perform basically 3D perform 3D reconstruction of the tourist site that has been visited. Okay, so in order to do that, you need to be able to triangulate points, and in order to do that, you need the extrinsic and intrinsic parameters of the camera. Okay, so I'll just show you the results, and then we'll talk about
all of the images on, so we can see where they all ended up. You see this kind of complicated picture of lots of photos in their own planes inside that model. Let's go dive in and find the photo that we were looking at. And now we can move back and forth among different photos, like this, just moving from side to side. These white boxes that are now appearing on the screen are showing where photos were taken. So, for example, if we want to close up over here, click on that, and you see that everything is registered perfectly with the three-dimensional model.
So you might ask, well, how were they able to do that 3D reconstruction if all they had was the photo? Well, the answer is that they did this. So they were able to estimate the fundamental matrix from a pair of photos, just as I showed you with my own holiday photos a couple of lectures ago. Okay, but then, in order to get the extrinsics, they needed the K. How did they get the K if no tourist was out there photographing, checkerboard patterns every time they took a photo? Well, because the wonders of technology, now if you take a photo with your camera, the camera internal parameters all get recorded in the JPEG metadata, in what's called EXIF. So in the EXIF data, you have the focal length of the camera and its optical center, which actually you can get away with usually estimating as being in the middle of the image anyway. And then you've got a K that's good enough to uplift your weak calibration with your fundamental matrix to a strong calibration to get your E, which then lets you do this reconstruction. So actually, this process of calibrating your camera with a grid, if you've got a camera that is instrumented to know its own focal length and the other internal parameters, you don't really need that anyway. Okay, but usually it's better to calibrate for accuracy. So just to summarize then the sort of flow diagram of the process to do a 3D reconstruction, or to get the camera parameters to do a 3D reconstruction or triangulation, your first step is for each viewpoint, in your epipolar geometry, so for your left camera and your right camera, independently, you need to get the internal parameters. How do you do that? By taking the camera and photographing a special object, like a grid, or looking in the EXIF data for the images you take. Okay, you've got a K then for each view, which was our K1 and our K2. You then take your pair of views and estimate your F using a weak calibration process, like the 8-point algorithm, or robustified version of that, like RANSAC version of it, which we covered. You then recover your E by performing the maths in a couple of slides ago, basically pre-multiplying and post-multiplying by your K for each camera. And then having got your E, you're able to then do whatever else you want to do. So if you're doing triangulation, you can exploit the fact that you can establish correspondence between points in this view and this view by just searching in a line, exploiting the epipolar geometry. You've got your corresponding points then, and you triangulate them using knowledge of your R and T and your K, using that purple box of equations that we covered when we covered the triangulation in lecture 22. That makes sense? So it all fits together, I hope. Right, any questions on that process at all?
Just one thing. Could you just go back to the point where you recovered K, first of all, from pi?
Yeah. Yeah.
Yeah.
Yeah.
Those, should that be obvious, or
there is a proof for it, but yeah, we're not covering it on this course. You may look in the textbook. I reference the Skolesky textbook to see the proof for that. Yeah. Any other questions? Okay. So then we might ask ourselves, well, having performed this calibration process, how can we measure how accurately we've calibrated our camera? And this is a useful thing to be able to do in a sort of production environment. Well, if we've recovered our camera parameters, our intrinsics and our extrinsics, via this sort of hybrid process of either getting EXIF data or our K and our fundamental matrix via this correspondence process, then it's going to be trivial to put together again this camera projection matrix by pulling those parameters in. Again, here's the equation for the camera projection matrix. I'll call this one pi prime because this is going to be a matrix that we have compounded together using this format that we've used all along, but this time we're populating our C with our estimate for T, our R with our R, our intrinsics there are in there, and our K is our intrinsics for that camera. So this pi prime is telling us how well we are, how well we're modelling the. Sorry, is giving us our projection operator that takes us from 3D to 2D using our recovered camera parameters. So what we could do is then take the images that we have used to do this calibration, or even some new ones, of our 3D object, and we can take those 3D points and we can push them through this projection operator. In other words, multiply them in homogeneous form by this operator to get their locations in 2D, and see how closely those 2D points land up to the actual images of those points in our photo. Yeah? And we can sum up the error, what's called the reprojection error, between where we think the point should be and where it actually is. And that gives us, we could take an average of those errors per pair of points and come up with an average error per point, which we call the reprojection error. Which tells us how good our calibration is. Does that make sense? Yeah? So we've got our multi-plane object, we've got our known 3D points on it in the coordinate system that this pi is reasoning about. We're taking further photos, or even the same photos we used to extract these parameters, and then we're basically feeding those 3D coordinates through this matrix, getting 2D coordinates, which should match up to the image of those points in our image, but probably will be slightly off. And we sum up how, the L2 distance, how far they're off, maybe divide by the number of points to get that reprojection error. Yeah. Okay, the final thing I want to say then, in terms of this material, is about stereo rectification. So, the way we've described the epipolar geometry, these cameras can be in any position, but often when we do capture stereo content, in other words, images of the world from two viewpoints, we commonly recover those photos with camera configuration that looks like this, where the cameras are side by side and their optical axes shoot out parallel into the world. And we call this the canonical camera configuration. Okay, so this is the way that 3D movies are shot. Okay, when you see people shooting with these 3D movie cameras, there's a lens and there's a mirror that's anyway, there's two cameras on a rig basically pointing forwards. So in this setup then, can you tell me what you think this tells us about where the epipolar lines fall? So if I'm talking about a point in the left-hand camera, and the epipolar line is, of course, the range of possible locations for that point in the right-hand camera, then what would that epipolar line look like? What way would it be pointing? Yeah, you got it right. Horizontal, yeah, that's it, absolutely, yeah. Why? How can we intuit that? Well, if we remember the epipolar line is the intersection of the epipolar plane with the imaging plane. If you look at this construction, okay, if these are parallel, then that epipolar plane will just slice through both of the image planes at the same level, horizontal. So a point is going to correspond to a line that's horizontal, level with that point in the other view. Okay. Well, that's very convenient because that really makes this a lot easier to perform matching, either by eye or computationally. So let's have a look at some data that's commonly used to measure the performance of such correspondence algorithms. So this is a highly cluttered scene. We like cluttered scenes in computer vision because there's lots of texture that helps us match. So if I were to pick a point, I don't know, like at the top of that lamp, in one view, like the top view, and then I went through so let's say the left-hand view, and I went through this right-hand view, and I wanted to find the corresponding point in this image. We know, because we're bound by the epipolar constraint, that we just have to search along the epipolar line, and we know now that the epipolar line is a horizontal line that is level with that point in the right-hand view. So actually, it's just a simple search along a scan line of pixels to find that point. We could cut a template from the first view, local to the point we want to find, and then just sweep that template along that epipolar line using something like a normalized cross-correlation in order to figure out the best location. And then we've recovered our correspondence. We don't need to worry about the fact that the images might be slightly rotated from one another because the cameras were non-parallel, were non-canonical. And we should worry about that because that would mean we'd have to do precision matching, warp our template into a different shape. If we're just doing something some matching in the canonical configuration, we just need regular, just square templates, windows to do that. Another really nice thing that we can do is trivially visualize the depth, in other words, the distance from camera of each point in the scene when we're in the canonical configuration. Okay, we know that from doing little experiments like putting a finger in front of your own stereo pair of cameras and opening and closing an eye, you see your finger moves left, right. Further away your finger is, the less it will move. Okay, we call that disparity. Okay, so if points are very close, then the distance between, the horizontal distance between those 2 points, having matched them, will be large. If the points are far away, then the point will match to a point very close to it. So that x shift between our two matching points, we can just visualize that directly as a heat map, which has been done here. The colors here are just different levels of disparity. They've just been color-coded for clarity. And you can see that it's easy to recover the depth of objects. So in this case, the lamp is closest, then the head is second closest, then the boxes, and then the shelves at the back. Okay, and actually, what we've done here on the top right is we just average the two images together, so you can see, they're obviously just blurring because we just averaged them on top of one another. You can see the disparity of the lamp and the head is much more than the shelves at the back there. So that's just what we're visualizing there. And there's some noise due to things like, you know, shiny parts of the object, specularities that don't obey that rule, yeah, because they're not, because the specularities move with you rather than with the stuck onto the object surface. Does that make sense? Okay, so, you know, quite often we will, if we want to do measurements about the world in 3 dimensions from a pair of images, we will shoot the content using cameras in a canonical form, or what we might do is warp the images so that they are in a canonical form before we then do subsequent processing on them. But the mechanisms for doing that warping are beyond the scope of this course, although basically it's estimating a homography and warping the images like we did for mosaicing. Okay, so let's end up with a quick exam-style quiz. Okay, so right, question 1: how can we estimate the camera projection matrix pi from a single view of known geometry? Okay, feel free to answer it. Okay, right, using the process we outlined today. Yeah, we have a known calibration object, so we define a 3D coordinate system. And we image those 3D points. So we've got 2D points. We've got correspondence now between points in the 3D world and our 2D image of it. And then we use 6 of those corresponding points in order to estimate our pi. How do we derive the extrinsics and intrinsics of a camera given our pi? Well, we can decompose it directly from the pi matrix, as we saw today. Or we can just decompose the intrinsics and use something external like a weak calibration for f in order to recover the extrinsics, as we've been discussing today. Question 3, I do want an answer from you on this one. Where in the 3D world are the extrinsic coordinates derived via, that are baked into that matrix pi? No. So pi here is the camera projection matrix for a single camera that we've recovered by taking a photo of a calibration object. So where is the origin?
The origin of that object.
It's the physical origin of that box, the corner of the 3D box. Yeah? So when we're calculating our R and our T, we're talking about where is the camera's focus in 3D, you know, what is the T that takes us from that origin, that corner of that box, all the way up to the camera's focal point. And then we're talking about the R that rotates our camera away from the origin of the world, which is defined by those 3 planes on the box, to the position it actually is. Okay. Question 4. Given 2 cameras of unknown intrinsic and extrinsic properties, how do we compute the fundamental matrix? Okay. Yeah? No? Go. Have a go.
We take a picture of the same object, we get like 6 matching points between the 2.
Yeah, 8,
we
yeah.
do an SPT over that.
Right. So, yeah, that's the 8-point algorithm. Okay, so we got 8 corresponding points between 2 views of an object, and we recover the f directly. And remember, the process for that is we use some noisy method like sieve correspondence to establish a whole bunch of points. We sample 8 of them, estimate the f for that, figure out the error against all of the point correspondences, and do it again and again and again, sampling that subset of 8 at random. It's the Ransack algorithm applied to the 8-point algorithm for estimating f. So that's our process of weak camera calibration. Okay, so given an f and 2 k's, one for the intrinsics of each camera, write down an expression for e. Right, so this is taking our f and then pre-multiplying it by the k's for each, which is our equation there on the bottom, yeah, for the essential matrix. Oops. Where in the 3D world are the extrinsic coordinates in E, that we've just recovered via that equation, defined relative to? Remember, we've got the E from our F, and our F was estimated from a pair of views this time, yeah? So that's relative to the left-hand camera. That's right, exactly, yeah. So the T in our E, the translation is the shift, is the baseline vector, basically. It's the shift of our right-hand center projection from the left hand. And the R is the rotation of the right-hand camera relative to the orientation of the left-hand camera. Okay, because in the maths that we went through for that, we assumed that the left-hand camera was basically the origin of the world, yeah? Okay, good. Okay, so in summary then, we've gone through the construction of the projection matrix and how it incorporates the intrinsic and extrinsic parameters. We've described how we can recover it with 6 pairs of points with a known scene geometry and their images. And we've shown how we can perform camera calibration, strong camera calibration now, with all the necessary derivations. We've also talked about how we can estimate the accuracy of a camera calibration through calculating that reprojection error, basically by recompiling that pie from its constituent parts and applying that as the projection from 3D and figuring out if the 2D images match up with what's in the image. And then finally, we just briefly talked about the canonical viewpoints and why people do this stereo rectification. Okay, and yeah, there's further information, as I say, in the Skaleski book on this. Right, that takes us up to 5:02, so let's have a 10-minute break and reconvene at 3:05. Okay, thank you.